So we're extremely fortunate to have Ananth here. He has spent the last 10 plus years, or five plus years, sorry, doubled it, 5+ years thinking about advanced technology and blockchain and machine learning, and thinking about privacy, security, and cryptography. So this is kind of the classics, I think, of your research. Okay, good. This is just a bunch of interesting things that you guys should know about and take into consideration when you're building your systems. So without further ado, here's Ananth.
Thank you. Thank you for that intro. And I hardly ever give talks with a mic, so let me know if you can't hear it or if I start moving too far away. Yeah, so I'm just going to talk to you about just a bunch of topics on privacy, security, and cryptography. I've been dabbling in all three. So a little bit of background, I got my PhD 4 years back now, and I've been doing research at Google Brain since then, working on each of these topics. So the talk is going to be as follows. So I was graciously given the stage to talk about a bunch of things that I know. And there are these three words that I often see being used and misused and interchanged. And I just thought, okay, here's when I'm going to get it off my chest. I'm going to explain to everyone here what confidentiality, what integrity, what privacy means, how they are different, how they're all important. And if there's anything you take away from this talk, just let it be at least this, that you can use these three terms in the right ways. Then I'll talk to you about data privacy. And I'm going to give sort of 4 stories or 4 projects, 4 ideas that were developed at Google and other places, and hopefully explain different aspects of data privacy and how to solve it. And I'm going to briefly touch upon data security. It's not really exactly my expertise, but I'll kind of point you to some things you should probably keep in mind. And there's a bunch of online courses that you should look at. So that's something I'll briefly touch upon. And finally, a topic that's sort of near and dear to my heart. So it's where I did my PhD, got in cryptography. Hopefully give you some really cool ideas that you can take away and so that you can have fun party conversations. And if you're kind of going to ask me what Ananth likes, or what sort of parties you talk about cryptography, well, then you're going to the wrong party. So there's some really cool ideas here. So let's get started. Okay, so confidentiality, integrity, and privacy. So in any crypto talk, you're going to have Alice and Bob. They're going to be talking something to each other, God knows what, but it's our job to protect their communication. So typically when you have something like this, you have Bob talking to Alice, and he wants to send her a message. Confidentiality talks about this adversary, this bad guy who's in the middle, who's listening on conversations. Confidentiality usually talks about whether this person can have access to the contents of the message, okay? So if you're worried about protecting the contents of the message, you typically say you're worried about the confidentiality of the data communication. Integrity is a different issue. In integrity, again, you have Bob and Alice talking, and you have a person who has access to the wire, has access to the communication channel. They try to change the message that's being sent, okay? Or in other words, they're also probably interested in impersonating who this person is. So they wanted Alice to think that she's talking to Bob, but they're actually just changing the messages along the way, and she's not talking to Bob. In fact, she's receiving messages from someone else. So if you worry about these sort of scenarios, that's what I typically refer to, or people typically refer to when they say integrity. Again, you can have confidentiality without integrity, you can have integrity without confidentiality. Ideally, you should have both. Now, what about privacy? So now you say, okay, what does privacy mean? So privacy typically talks about people participating in a scenario where there are multiple people pulling their data. So if you're the only person who's showing up for a survey or sending information to someone, you really don't have privacy. You're the only person there. If you're the only person who voted for election, then it's pretty clear sort of what you voted. So the scenario usually involves multiple people participating. So here you have 3 people. They send some message to some data curator. She wants to do something cool with it. What does she want to do? Maybe she wants to compute some function. Maybe she wants to compute some statistics. Think about your census surveys and so on. Privacy is worried about what a person can find out looking at this computed value, this aggregate value, about your individual piece of data. So is there a pointer here? Oops, I guess not. Okay, so it talks about what the adversary can find out, given the sort of the function evaluated on all the individual's data, what they can find out about your particular piece of data that you contributed. So that's what privacy is about. Okay, so I hope you understand the 3 different aspects of data protection, and you need to worry about all of them, and they all have different techniques. Okay, so let's talk about privacy. So this is going to be the first section of the talk. So privacy, one of the key ideas in privacy is something called randomized response. I'm just going to walk you through what it is. It was a technique that was developed by statisticians in the 1960s. It was used for very sensitive surveys. What kind of surveys did they conduct in the 1960s? Well, they were really worried about whether people were members of the Communist Party or not. And if you have actually come into this country, if you're immigrated and you have kind of filled out paperwork, then they still continue to ask this question for some reason or the other. So people wanted to know sort of something sensitive. This is a sensitive piece of information they want to find out. And they actually want to compute honest or sort of accurate surveys, because if you sort of incentivize people not to tell the truth, you're not going to get the actual information out. So what do? So they said the following. So imagine, for the purpose of this slide, the green value represents someone who's not a member of the Communist Party, and red value represents a member. So green is no, red is yes. So imagine this person wants to say no. What they do is they actually toss a coin. So dollar here is going to refer to a coin toss. It's going to refer to randomness. They toss a coin, and if the coin lands heads, then they always say yes, okay? So independent of what their true value is, they end up saying that yes, I'm a member of the Communist Party. If it lands tails, then they give the true value, okay? So this is how they behave. So depending on whether you say yes or no, if you toss a coin, if it lands heads, you always say yes. If it lands tails, then you say the true answer. Okay, now is this useful? Can you actually do something with data collected like this? Yes, it is useful. There's like a homework problem. Imagine you have some bias for the coin. So here, imagine it's 50%. Then half the answers are going to be false. So half the answers that say that yes, I'm a member are actually not going to be true values. So you just eliminate that half. That's the minus n over 2. So the rest is basically the true numbers reported minus the rest, minus n over 2 is going to be the actual answer. So if 70% of the people said yes to the survey, then the real number is 20%. So what am I trying to say in all of this? I'm basically trying to say that adding some noise or adding some sort of randomization still lets you compute reasonably accurate statistics. Now, how does this help with privacy? Well, imagine a person has access to your report. So they say, hey, I noticed that you said yes to this survey. This is a problem. You and I have a problem. Well, it's very difficult for them to say whether you actually had a true value yes or had a true value no, right? You can always claim, no, I tossed my coin, it landed heads, and that's why I answered yes. Actually, the real answer is no. And there's no way for them to distinguish between these two scenarios as to what happened. The only way they can distinguish between the two scenarios is if they have access to your coin toss, right? If they have access to your secret information. So this in one slide sort of tells you a little bit, gives you a flavor of how we typically protect privacy. The idea being that you use some randomness, and this randomness needs to be protected, needs to be hidden. And with the randomness being hidden, you can actually have some sort of plausible deniability. You can claim that your answer was something else. But at the same time, if everyone follows the protocol correctly, and the randomness is used in the right way, so like in this case, the coin is biased 50%, then you can actually get accurate statistics at the end of the day. Now, what happens if your answer is yes? If your answer is no. So in this case, you see that the no option is not being protected. So if someone is on the street and they're like, oh, you said no, then you're clearly not a communist. So your data is being leaked if someone found out your particular answer. So that's what, so this is done in the 60s, and this is sort of a slight modification of this protocol where when you choose to lie, so when the kind of coin toss lands heads, you answer yes or no with some probability again, right? So you choose to lie, sort of roughly half the time you say yes, half the time you say no. So this way, both answers are being protected. If you said yes, maybe you actually said yes, maybe you actually said no. If you say no, maybe you actually said yes, maybe you actually said no. And again, it's a small sort of homework problem to figure out if you had this kind of protocol, how would you actually get the real answer out of it? And by doing this, it gives you something called differential privacy. So differential privacy, you might have heard of this term. And if you're wondering what it is, well, this is one example of differential privacy. It's something called local differential privacy. So all the privacy is added locally. But this has become a gold standard of privacy. I encourage you to look at it when you have a lot of data and you're worried about people's privacy. Privacy is a very tricky concept. I think back in the 80s and 90s, they had notions of privacy called k-anonymity, which you might still hear being referred to. There are a lot of challenges with it. It took 10, 15 years of attacks and sort of different analyses to land on what we call now the gold standard. And this is about 12, say 13 years old. It's being used widely everywhere in the last few years. So Google's own Rapport project, which I was part of for a while, deployed this in Google Chrome browsers. Apple, Microsoft, Mozilla, a bunch of other companies are following suit. So this is a very, very simple idea from the 60s that's actually being used today to collect data while retaining the privacy of individuals. And they're doing something very similar to this. You kind of already know half of what's going on. So this is my sort of first piece of advice. Is to use randomness to perturb data when you can, and you can actually do so without hurting its utility if you do it cleverly. There's a bunch of papers. I think the slides will be online, or I can just give the slides to the organizers, and you can kind of take a look at all the details. Because I'm going to be covering a bunch of topics, I'll sort of give some bibliography from time to time. The next interesting idea that you guys should know about or might want to keep in mind is something called PROCLO. This is a recent work that we did out of Google. It's a combination of two words. So it's privacy and oklo. Oklo is the Greek word for crowds. Anyone here from Greece? Okay. So oklo is the Greek word for crowds. So like think of ochlocracy and so on. And the idea is if you have a crowd of users and typically you're not worried about where the data came from, then you can actually use that itself to protect people's privacy. In other words, you can design your setup or design your system in a way that people can disappear, can blend into crowds, and that can give you some sort of privacy. What do I mean by that? A little more precisely, imagine you have some data collection task. You have a bunch of users. They want to collect pieces of data. what do you do nowadays? You just simply send all of it to some curator, right? At the end of the day, so the curator here says, okay, you contributed three reports, and they're like red, and green, and you contributed 3 different reports, and so on. They collect all of this data, they do their analysis. Maybe you're worried about how many people are having bugs with the software. Maybe you're worried about how often people use the software, and so on and so forth. You use this sort of data. It turns out that in a lot of scenarios, you actually don't need to know whether this particular person reported 3 values or not. You don't need to know whether the second person reported the same value 3 times or different values 3 times. Imagine you're computing popular URLs, so just kind of things that we do at Google. You really don't need to know the details of specific aspects of a user's behavior. In that case, what we suggest is to do the natural thing, which is you add infrastructure in the middle that actually ends up shuffling all of these reports. So if you shuffle all of these reports, what you end up getting at the end of the day are these bags or these kind of like crowds of reports. And the idea is that each individual's contribution is still there in this crowd of reports, but the attribution is lost. You don't know who's reported what, or whether the same person's reported the value twice, or they've reported 2 different values. And often you'll realize that you don't actually care about this sort of specificity of where these values are coming from. And then for privacy, you add some noise. You can throw away a couple of reports without actually affecting the entire story that you're telling. And you end up getting this kind of almost the same set of reports that you got before, but now there's a little bit of perturbation that's going on, and you don't know exactly where they're coming from. You just have these crowds of reports to work with. So what we show in the paper is that this actually gives you much better utility and privacy trade-offs than doing everything locally. The only catch is you need to have this middleman. You need to have this infrastructure. But the idea is use the power of crowds to improve privacy. If you're storing data, if you want to keep data around, try to remove attribution as much as you can. It's not really going to be useful. But mathematically, even you can actually prove that these things add privacy. They actually make sure that the fact that you can hide under a crowd of data gives you some more privacy than if you didn't have that, if you had sort of naked attribution. So this is a paper that we published last year. So I'd encourage you to take a look at it. And then now, of course, I hear that there's a lot of machine learning that's common to everyone who's here. And people want to do machine learning on all sorts of data. So let's see how we can do it with privacy. And here I want to distinguish between 2 scenarios. One is privacy for the training data, and the other is privacy at inference time. So I'm only worried about privacy during the training stage. And I think this is more useful, especially for big companies, because we have sensitive information. We have information that you'd like to work with without the expense of privacy. So there are going to be 2 broad approaches here. So one is called a white box approach, and one's a black box approach. Again, there's not enough time to go into all the details, but I just want you to know that these technologies exist out there. So let me briefly explain how this works. And if you know machine learning completely very well, this is going to be a very sort of naive, silly overview, but I don't know a lot more machine learning than this. So machine learning typically works as follows. So you have a model, and the model has parameters that's sort of represented by this value theta here. And typically you take the model, evaluate it on your training data, you see what your loss is and how badly or how well it's performing, and then you try to improve the model taking steps at a time. And this is called gradient descent. You try to take the best step that you can at every stage to make sure that your model sort of gradually and slowly improves until it hopefully converges or until it gets good enough on all the training data that you have. And then you hope it does well on the test data. So there's this loss function. It's on a very complicated surface or manifold, and it keeps going down. So each time you take this gradient descent step, how do you take this step? How do you make sure that you go in the right direction? Well, you do so by looking at inputs from user data, right? You look at an input, you see how it performs, how the model performs on this data, and then you take a step. And this is where there's a privacy leakage is happening. So this is where your model output depends on input data. So now the question is, okay, how do we avoid it? How do we make sure that individual inputs are not terribly influencing or not highly influencing the model? Well, there is one hammer that we have, which is what? Which is noise. So we try to take these steps with some noise. So in other words, we don't take these gradient steps exactly as you would compute, but we add a little bit of noise, we perturb it a little bit, and we continue to do the training. There's a lot more work that needs to be done, but this is basically the idea. So if someone comes and says, hey, how do you do sort of machine learning with privacy? The answer is you do gradient descent, but you make it a little noisy along the way, and hopefully you get good accuracy and privacy at the same time. That requires a lot of research. Google has some expertise. Again, we're writing some work. I think we are working through the process of, I think we have some code that's open. We definitely have ideas that are out there. So I'd encourage you to kind of talk to us if you need to know more. So you can do this at white box. And I call this white box because you actually have to sit down and fiddle with the model. You have to figure out how the model is doing its steps, how it's consuming user data, and so on and so forth. Maybe you don't have that much time or you don't have the patience. What you do have is a lot of user data. Okay? What you do with this is you can train machine learning models with privacy without having to know exactly what's going on sort of under the hood. And the way you do it is as follows. You take the user data, you partition it into a bunch of blocks. You train individual models on each of these partitions of data. Okay? You train these models individually, separately. So these models have nothing to do with each other. They don't know what's going on in the rest of the partitions. Then what you do is you do the following. So if you know machine learning, you know that one of the cool things about machine learning is it's really easy to transfer knowledge. So you train models on one aspect of data. It's very easy to actually transfer this knowledge to other domains. Machine learning models have these sort of knack that let you do this. So we use sort of this aspect of machine learning, and it's called transfer learning. We transfer this data, transfer this knowledge to what we call a student model, and the student model here acts on public data. Okay. Now the key here is that it doesn't just simply ask these models for, hey, how do I label this public data and how do I get better at my machine learning task? What instead it does is it talks through an aggregate teacher. Okay, the aggregate teacher looks at all the teachers, how they respond to these inputs, and then gives it one value. And here is where we add noise. So you should have stopped and thought, hey, where are we adding noise to this process? How are we making sure that the inputs are not directly influencing the output, which is where you have privacy problems. So it turns out if you do this step, in other words, you train models individually, have this aggregate model that sort of doesn't exactly give you the right answer all the time, but mostly gives you the right answer, sort of changes the votes from the teachers a little bit. And then if you use this to transfer knowledge from what we call the teacher models to the student model using public data, then this final student model that is trained has privacy. And notice here, I didn't tell you anything about the architecture that we are working with. I didn't tell you whether it's a convolutional neural network, whether it is just some old-fashioned model that's being trained, and so on. So that's the key idea. You can do all of this in a black box way. So these are two broad approaches to doing machine learning with privacy. And some of them work in some scenarios, some of them don't work. If you have a lot of data, maybe the second scenario is easier. If you have a lot of compute, or if you have really high quality data, perhaps the first one is much easier to work with, because in the sort of the noise really doesn't matter that much. So there are a bunch of ideas here. And yeah, the only advice I can say is use these techniques if you can, if it's applicable to you. And here's some papers from our group in the last 3 years that sort of talk about this. And again, I'll give you all of this information in the slides. Finally, the fourth vignette about data privacy is going to be something called federated machine learning. And you might have heard this term crop up in the last few years if you haven't. Federated machine learning is a very nice idea. I'll try to explain it to you in one slide. Federated machine learning says the following. It says, typically you have, say, things like mobile devices that send data upstream. And there's a company like Google that collects all of this data, does some really cool machine learning. That's what the brain is supposed to represent, and then spits out this model. Okay? This is the typical way in which machine learning happens. What if instead you did the following? So you usually have good models out there already, and you just want to use the data to improve the models. So think about you have sort of models that predict what text you're going to type on your keyboard, and you still want to probably improve the model a little bit with sort of data that you're contributing, but you don't need to collect all the data and train it completely from scratch. So in these scenarios, what you do is the following. So you actually take the model, you push the model down to devices, and then you use your local data to actually do machine learning locally. So in other words, you end up computing what are called local updates to the model. So I have my own data. I'm not giving it out there. I'm taking the model in instead, and I'm trying to see how to sort of improve the model. How would I update the model if I was training it on my own data? And the reason this is called federated is so that you have access or you have control over your own piece of information. All the learning and all the data computation happens locally. Then what do you do with these local updates? You don't have a model yet. You just have local updates. What do you do with it? Well, you send all of these local updates upstream, and then Google or an upstream server is aggregating all of these updates and updating the global model. And then you push this model back down. You could do local updates again, and then you rinse and repeat. So this is what we mean when we say federated machine learning. And what are the advantages? Well, the advantages are data stays local, compute stays local, and you can kind of contribute your information only as much as you feel like you want to contribute, or as much as you feel is necessary. You don't fully get privacy for reasons that are technical, and I won't kind of get into the details. I'll just say that these local updates themselves can leak some information because they're kind of like the gradient steps themselves. So this alone by itself does not give you privacy in the same way that the previous slides sort of gave you privacy. But you can throw some crypto, you can throw a little bit of machinery, and you can actually make it completely private. So that's sort of a useful idea. So I want you to think of this picture and think of federated machine learning. And keep compute and data local when you can. So more often than not, or in a lot of scenarios, it is possible to actually keep data local to sort of make updates locally and don't really have to send it upstream. And that provides you privacy. Here's a couple of papers. Again, you can kind of take a look at it offline. If you want to know more details about how to do this, there's some really cool machine learning models that have been trained and some very interesting crypto that's there. So, okay, so that's sort of privacy in kind of 4 stories. So I hope you have a flavor of what is local differential privacy now, how do you do private machine learning, what is federated machine learning, and so on. Security is going to be much simpler because it's not my expertise, it's not my area of sort of research. There are a lot of online courses, and I'm kind of being a bit biased here because I went to Stanford, but this is a really good course. I encourage you to read it. So some of you might already know some of the contents on the slide, so that's pretty cool. The first thing that you would want to sort of read is this beautiful essay called Reflections on Trusting Trust. How many of you have heard of it or read this essay? That's great, yeah. So Ken Thompson is a Turing Award winner, and he wrote this essay for the ceremony, for the Turing Award ceremony. And what he talks about in this essay, it almost becomes a philosophical question. So it's a question that says, so what do you mean by security? What do you mean by actually trusting software? So you can think about security of, okay, maybe the code you write. So you look at the code and you think, okay, maybe it's secure, but then you trust the compiler. Then you're like, okay, I'll have my own compiler. I'll sort of compile it from scratch. Then do you trust the platform under which you're compiling, and so on and so forth. So this is an essay that captured all of these ideas, I think in the 70s or 80s, if I'm not mistaken, which kind of comes down to the fact that security is a very philosophical concept. And also, it's very important for you to define trust boundaries. So define sort of trust domains and operate under those trust domains. If you try to get absolute security, it's not going to be possible. But at the same time, it does not mean that you can meaningfully improve security by just adding, kind of by doing the right thing. So you might have heard this advice. And if you haven't heard this advice, well, hear it now. Is don't roll your own crypto or security infrastructure. There's a good chance that you might get it wrong. A lot of work goes into actually getting it right. There are a lot of subtleties and difficulties. And I think there are good public libraries out there, especially by companies like Google, who are trying to make sure that people have access to good quality code. Cloud is also doing a good job. So kind of security is much easier to solve with scale. So if you're taking advantage of sort of big cloud infrastructure providers, then the security is usually much better than kind of having your own servers and keeping tabs of the latest exploits, kind of worrying about whether they're using the right versions, and so on and so forth. This is sort of my idea. This is kind of my advice. And you should know about exploits and defenses. This space is pretty cool because all of these exploits are like neat puzzles and neat hacks in the literal sense, and there are defenses that try to defend against them. You might hear some of these terms. This is what they mean. You might deal with legacy code. I encourage you to sort of know at least the concept of sort of sandboxing and isolation technologies and use them well. If you have anything that's internet facing, I'm sure you know about HTTPS. You need to worry about all of these aspects of internet privacy. It's a whole beast unto itself. Denial of service attacks, if you don't know what they are, so it's just basically being overwhelmed by requests online in such a way that your servers come down and crash. And there are actually services that provide you this protection. Again, if you're operating on the cloud, usually have good denial of service protection. There are a lot of going to be cool attacks and cool sort of the latest kids on the block. People are going to have always exciting attacks. The latest are Spectre and Foreshadow, which talk about speculative execution on the Intel platform. It's really cool stuff, but you probably don't need to worry about it too much. Just kind of keep tabs of it and update your code as quickly as you can. And there's always going to be more newer and cooler stuff that happens. And then finally, I have not spoken anything about mobile because I don't know anything about mobile. So there's a whole mobile space out there. Again, a lot of these aspects apply to mobile infrastructure, mobile security as well. And it's good for you to keep in mind or have some experts, or at least talk to experts, or use sort of standard technologies or standard toolkits so that some of these are automatically taken care of for you. So that's about it. I'm not going to say anything more about security, but I encourage you to kind of look online. There's some really good courses, really good little sort of ways to improve your own security and intuition, and they're fun. Okay, now sort of the stuff that I really enjoy, which is cryptography. So cryptography is sort of comes from the Greek word, which is basically the art of making secrets and keeping secrets. So it's like one of the coolest things you can do, I think. Again, I'm a bit biased, but it's a lot of fun. So we talked about confidentiality and integrity right in the beginning, right? So I'm going to kind of come back to it by showing you how you can actually get confidentiality and integrity. You get confidentiality, that is, you get the data protection by what is called encryption. There are two flavors of encryption, symmetric key and public key encryption. I won't go into the details about what each of them refer to, but if you ever hear the terms AES 128.256 or elliptic Diffie-Hellman ephemeral, that is ECDHE, or El-Gamal, you know what I'm talking about. You're talking about techniques, encryption techniques, that are used to protect the confidentiality of communication channels, okay? And integrity is protected by something called MACs, or message authentication codes, and signatures. And they're again like this sort of symmetric key and public key variants. I won't get into the details of what that means, but there are two different variants of them. HMAC SHA-256 is something you might hear. SHA is a hash function. HMAC is called hash-based message authentication codes. This is commonly used. Hopefully you're using it under some sort of library somewhere. Signatures are elliptic DSA, digital signing algorithm, and RSA, which are things, again, you might have heard of these terms. So now you know they mean you're protecting the integrity of your messages. In other words, you're making sure the messages cannot be modified or manipulated, or the source of the messages cannot be changed by eavesdroppers, by adversaries. And more precisely, what confidentiality lets you get, and kind of pictorially, I like to represent this pictorially, is it sort of lets you put your message in a sealed envelope. Okay, that's an encryption. And what does this buy you? Well, for someone who's on the wire, they can look at two different sealed envelopes and not really figure out what's going on inside envelopes. So they wouldn't be able to tell a red envelope from a blue envelope, and that protects the contents of the message. How do you protect the integrity of the message? Signatures they look like signatures that you normally use to sign documents, right? So they are appended to the message. They say nothing about the confidentiality of the message. In fact, a signed document, everyone can read it. But what it ensures is that an adversary cannot sort of give a blue signature for a red message. So in other words, they cannot take a signature that's already signed and sort of change it in a way that it seemingly signs another message without, of course, having access to the keys involved here. And you always need to have keys here. You notice that suddenly keys showed up in these images, and without having keys, without having secrets between the two parties, it's very difficult for you to do all of this. Okay, so that's sort of just getting it out of the way, how you get confidentiality, integrity, how you get privacy. So now you addressed all the problems. So now let's just have some fun, okay? So, so there's some three very nice ideas again I want you to take away from this talk. I think they're useful. They may not be immediately applicable to you, but I think it's still really cool for you to know, and it might be useful. So they're going to be secret sharing, secure multi-party computation, and zero knowledge proofs. So just sort of a show of hands, I'm curious to see anyone who's heard about any of these terms before this talk. Okay, that's great. So what terms have you guys heard? Just, okay, same? So do most people here heard of zero knowledge proofs? Okay. Well, for the rest of you, you're now going to hear about zero knowledge proofs at the end of the talk, and it's going to be really cool. But first, let me tell you about secret sharing. So secret sharing is sort of one of these really, really amazing ideas that's so obvious in hindsight, but it kind of takes a genius to actually arrive at. And you know it's amazing because it's very easy to explain. I'm going to explain to you in 2 slides. And the original paper is actually just a 2-page paper, which is amazing. Like, it's a dream of anyone who's writing papers to write a 2-page paper and actually get it through. It was published in 1979 and it's used widely in cryptography. Adi Shamir, by the way, won also Turing Award for his work in cryptography, and he's the S in RSA. So it's a pretty nice idea. The idea is as follows. It says, imagine you have a secret here. I don't care for what purpose you want to use the secret for, but you have a secret. What you can do with the secret is you can split it into what are called secret shares. So the idea is you can take a secret and you can generate shares of the secret. In fact, you can generate as many shares of the secret as you want. And what do these shares do? Well, they have a very nice property. The property is as follows. So let's assume that you're just picking the number 3. So you're kind of doing the secret sharing with number 3 in mind. So it says that you can take any 3 shares, okay, and you can reconstruct the secret. And this is true for any combination of these 3 shares. So you can generate as many shares as you want, so the way that 3 shares recovers the original secret. But if you have, and that's called T secret sharing, or like 3 secret sharing. But the moment you have only 2 secret shares, and again, this could be any of the 2 secret shares, that reveals absolutely zero information about the message, about the secret, okay? So if you have just 2 shares, for example, the first and the 6th share, no matter what you do with the shares, you're not able to tell whether the underlying secret is a blue secret or a red secret or a green secret and so on and so forth, right? This is a pretty interesting problem, and like maybe you can think about it for like 30 seconds or even less as I just keep talking as to how you'd actually do this. So like what would be the idea that you could kind of take a secret, split it into multiple shares in such a way that you cannot combine them? And again, it's just easy to do. Suppose you can take a single secret, split it into 2 parts, okay? And then you can say, okay, if you have only 1 part, you obviously don't have access to it, but if you have both parts, you have access to it. But the really cool idea that sort of propels a lot of crypto is you can do this for any arbitrary set of, say, 3 shares or 4 shares and so on. So that's the really nice idea. And the solution here, and again, some of you might know this, is by using polynomials. So what you do is you choose a random degree t minus 1 polynomial, and a polynomial here is just this sort of abstract mathematical object that you can evaluate, and typically has a variable like x. You can evaluate it in this way. And you set the 0 coefficient to be the secret, okay? So you pick a random polynomial. So a and b here are just random values that you choose. And usually you have the polynomial as ax squared plus bx plus c. Here the c here is going to be the secret that you chose. Then what you do is to evaluate your secret shares, you just simply evaluate this polynomial, okay? So secret share number 1 is just simply p evaluated on 1. Secret share number 2 is p evaluated on 2 and so on. So you can just kind of keep evaluating it on as many values as you want, and you keep getting a lot of secret shares. When you evaluate it on 0, something special happens. So ax squared and bx, they disappear, and you're left with the secret. So this polynomial is sort of encoding the secret, but in a way that you can kind of reveal parts of it or reveal fractions of it by just evaluating it on different points. So if you protect the polynomial, you're protecting the secret. If you reveal the polynomial, you're revealing the secret. How do you reveal the polynomial? Well, if you have 3 points and you have a degree 2 polynomial, then sort of high school math or college math will tell you that you can reconstruct a polynomial of degree 2 with 3 points. And this is true for any arbitrary degree. So if you have like a degree 5 polynomial, then you need 6 points to evaluate, and then you get a 6 secret sharing, as opposed to like a 3 secret sharing. So, and this doesn't matter what 3 points you evaluate on, so long as they're different. Then you end up getting sort of P of x. And with P of x, you can recover P of 0. And with P of 0, you can recover the secret. You're done. What happens if you have just 2 points in this scenario when like you have a degree 3 polynomial, a degree 2 polynomial? So with the 2 points, you really can't exactly pinpoint a parabola that passes through these 2 points. So there are an infinite number of curves that actually passes through these 2 points. And each particular curve represents a different secret, right? So now you have these 2 points. You know a polynomial passes through these 2 points, but it tells you nothing about the 0 value, about where the polynomial sort of hits the y-axis. So that is like completely and entirely hiding the secret information, which is a pretty cool idea, right? And that's all there is to it. So this is all of secret sharing. This is all there is in the 2-page paper, but it's probably been cited literally like tens of thousands of times. And it's used all over in cryptography. Okay, I hope you understood this. It's a really nice idea that I like. The second idea that I'm going to talk about is, again, one of these words that was like purely in the academic domain for a while, but in the last 10 years or so, slowly becoming more and more practical. Google is actually doing some things with secure multi-party computation, as are many other companies. I'll just explain to you what it means, and I'll briefly touch upon what it can do, but I'm not going to go into any details because it's very complicated. And I think you've gotten sort of enough technical details out of one talk. Secure multi-party computations is the following. It says you can have 3 people with 3 secrets or 3 inputs that they have that they want to protect. So here you have Bob with the blue input, Charlie with the green input, Alice with the yellow input. And they end up talking to each other in a way, in a protocol. So these are typically protocols that they follow. And at the end of it, each person ends up computing a function that they want on the other people's inputs, okay? So at the end of the protocol, you have Bob computing f of 1 on his input, Charlie's input, and Alice's input. Similarly, f of 2 and f of 3. But at the end of the protocol, the cool idea is that the only thing that these people learn is the function that they want to compute. They don't end up learning anything else. In particular, Bob doesn't know what the green value is, insofar as he can kind of figure it out from the function evaluated on the green value, but he doesn't know what the green value is. Similarly, Charlie might know what the green value is because it's his input, but he doesn't know anything about Bob's blue value. And he only knows F2 of of the inputs that are communicated. And similarly, this person. What do you mean by like they don't know anything else, or the protocol does not reveal anything else? So this is a very tricky notion, and in fact, like it took a while for people to figure out how to actually precisely state this. What it means, sort of the way to think about it is, what you want to say is that, or what you can demonstrate mathematically is that if you're only given this blue value and the output of the function f1, then you can sort of simulate the entire transcript of the protocol as far as Bob is concerned. So you can kind of say, oh, this is what he sent, and this is what she sent, and this is what they sent at the end of it. And Bob will kind of look at it, squint at it, and be like, yeah, I guess this could be a real protocol. I guess this is what could have happened. And you could kind of do this. You could run the simulation entirely without knowing any of the other values, just knowing kind of Bob's own inputs and the output of the function f1. What this is telling you is that this entire protocol, as far as Bob is concerned, really didn't reveal anything. If someone could kind of come up with the same protocol, just knowing his input and his output. So that's what the secure part of secure multi-party computation means. And it's a slightly tricky concept. This whole concept of simulation kind of sometimes gives you pause. But this is this is how cryptographers usually prove these kind of things. And how do you do this? Well, does anyone have any answers? So this is kind of like one of these Chekhov guns or something. So the answer is you do actually use secret sharing. So just what I said in the previous slide. So secret sharing is actually one of the bases where you can kind of split up your values into secrets. People can end up computing on these secrets. And then finally, when they combine together, they only end up getting the combined value of sort of whatever you did on these secrets. And nothing in between is known because you're still operating with secrets. And as long as you don't have enough copies to put together, it could be junk for all you know. I'll leave it at that. I won't get into more details because it's more complicated. I won't talk about different notions of adversaries. Here we assume all of them are honest, but they're kind of curious. They just want to know, okay, what else is going on out there? Sometimes we might worry about malicious adversaries. And by that, there are adversaries that sort of change the protocol. Then you have ideas of can you protect against changes, or can you at least detect changes? So there's a whole field out there that builds up on this key idea, the simple idea, and then makes it sort of more robust. Okay, what do you do with multi-party computation? And this just requires a little bit of imagination because technically you can sort of do almost everything with multi-party computation. Like anything you want to compute on data, you can do it with multi-party computation. But more practically, you can have notions of this for two parties, okay? So two honest but curious parties. And then you can actually share your data with other people that you don't trust in a way that the final product that is computed is something that's common to both of you. So maybe you have some set of customers you want to share, the other party has some set of customers you want to share. You can share your customers that are common without actually revealing more, without actually kind of leaking information that might be harmful to one of the two companies. Of course, you do this traditionally through enforcing them through like bulletproof contracts and so on and so forth. But this is a technical way in which you can achieve these. And also it turns out that if you run multiple services, so imagine you're a big company like Google, and you're actually running these services separately, then you can actually take user data and actually split them up into these services, do everything in a multi-party sense, and as long as these servers don't kind of talk to each other through back channels, they only talk to each other through this protocol, you actually preserve users' privacy. And of course, there's like some work that's being done in Google with regards to the first aspect. Again, I won't get into more details. There are companies that are doing this. Most famously, if you want to kind of go and Google something really cool, it's called the Danish sugar beet auction, if I'm not mistaken. So Denmark actually had 3 teams evaluate a complicated protocol to auction off their sugar beet something or the other. I don't know if it's land or if it's prices or whatever. And they did this back in 2008, so they're actually like way ahead of the curve. And they demonstrated that you could actually run a multi-party computation protocol, and you could run it with like Danish farmers. So it's like, it's really, really, I mean, it's just one of these funny anecdotes, but people are using it more practically for some things like this. And then finally, kind of the last topic today is going to be on zero knowledge proofs. Okay, so some of you already know what this is about, but for the rest of you, this is one of those concepts that almost seems impossible. It kind of seems like it is, like at the end of this talk, you might go back and be like, hey, did he like kind of pull a fast one on us? It's like is what he's saying really true? Is it like a big joke like that cryptographers say to everyone? But no, what it actually is this very, really nice idea that says that you can have 2 people who are called a prover and a verifier. The verifier has some sort of, say, let's say a public statement or a public value that has some secret associated with it, okay? I'll leave it a bit abstract, but I'm going to go through an example so you understand better what's going on. And the verifier cannot compute the secret from this public value, okay? So she knows that there's a blue message, and that this blue message will kind of match with this public value that she knows, but she doesn't know what it is. Here comes a prover and says, hey, you know what? I know this blue message. And it's like, okay, cool, show it to me. And the prover says, no, but I'm not going to show it to you because I want to protect it. It's sort of my confidential information, or it's my secret. But I want to convince you that I know that I actually have the secret, without telling you what the secret actually is, okay? So they can run a protocol, and at the end of the protocol, oops, so there's some misalignment, but that should read, the verifier is convinced that the prover knows this blue value and does not learn anything else at the end of the protocol, okay? So they can talk to each other, and at the end, the verifier can come away with some confidence saying, aha, yeah, I agree that Bob knows the blue value, but she doesn't know what the blue value actually is. She just knows that he knows some secret that corresponds to the public value that she has. More precisely, what do you mean by is convinced? It means that the cheating provers, so someone who claims, oh, I have the blue value, but actually they're working with the red value, they really don't know what the blue value is themselves, they cannot convince a verifier by running this protocol that they actually have the blue value, okay? Also, this is useful only if you can kind of go from this, you can't go from this public value to the secret value very easily. If it's very easy to do it, then you don't need to worry about sort of zero knowledge. You just don't care about whether the verifier has learned the blue value or not, because anyone can learn the blue value. Okay, so this all sounds very abstract and, like I said, very vague, and it's like I feel like I'm pulling a fast one, but so let's get more concrete. So imagine the public value is sort of two spheres that are out there, and these 2 spheres are actually colored, but let's imagine for a moment that the verifier is colorblind, okay? So they do not have the ability to detect which spheres are which color. The prover comes along and says, hey, I know what the colors of the 2 spheres are. I know that one is a green sphere and one is a blue sphere. Of course, I can tell you this is the green sphere and this is the blue sphere, but I don't want to. That's some secret information I want to hold. Can the prover convince the verifier that they know the colors of the 2 spheres without actually revealing what the colors are? Okay, so this is like a party puzzle, party trick, and you can do it with zero knowledge. What you do is as follows. The verifier takes these 2 spheres and she places it in her sort of left hand and right hand. Okay, and she tells the prover, hey Bob, like I have these 2 spheres in my left and right hand. I want you to pick one of the 2 hands, and then you're going to tell me what happens with that, with the ball, with the sphere in that hand. So imagine the prover picks the left hand, okay? And then what she does is she takes the spheres behind her back, and then she actually shuffles them. So she knows whether she swapped the 2 spheres around or she's kept the 2 spheres as they are. No one else knows what's happening. And then she presents these 2 spheres again, okay? Now what can Bob do? Bob can tell exactly where the sphere on the left hand went to, right? They can just look at the color and say, okay, if it kind of stays in the same place, then it stays in the left hand. If it's gone to the right hand, then she swapped the 2 balls around and it's actually in the right hand. So they can respond with this value left or right, and Alice can use this to verify whether Bob is kind of telling the truth or not. So sort of more pictorially, imagine if she actually ended up swapping the two spheres, then Bob can say, okay, so the blue sphere is on the left, now the blue sphere is on the right. The blue sphere is on the left, or the blue sphere remains on the left. So he can say this 100% of the time. But what about someone who's cheating? What about someone who doesn't know the color of the spheres, is also colorblind, but somehow trying to trick Alice into thinking that they know the colors? So, well, they don't know what's going to go on, and they're going to succeed with 50% probability. So they're going to know half the time they're going to guess it right, half the time they're going to guess it completely wrong. And if you run this multiple times, then you can really, really be sure whether Bob is telling the truth, whether Bob actually knows what the colors of the two spheres are, or he doesn't. He's just bluffing. He's just pulling, he really doesn't know what's going on. And this is an example of a zero knowledge proof. And the key idea here is, okay, now let's step back and be, okay, you're kind of somewhat convinced that a cheating prover cannot convince a verifier. But what has a verifier learned in this process? Has Alice learned anything about the colors of the two spheres? No, she knows that they're different colors, but that everyone knew that. Can she go and convince someone else that this is a green sphere and this is a blue sphere? No, she can't, because she doesn't have access to that knowledge. That knowledge has somehow not been revealed. What has been revealed is the fact that Bob has that knowledge. Okay, so it's a slightly different thing. So that's what we mean by zero knowledge proofs. And there's also this really nice, I don't know if it's in Wikipedia or not, but there's this really nice book, I think, or an article that was published on how to explain zero knowledge to your 5-year-old. So you can actually do this Where's Wally or Where's Waldo, this sort of puzzle book that they have. And you can actually kind of find out where Waldo is. And of course, your 5-year-old is not going to believe you, or they're going to kind of want to know where it is, but you don't want to spoil the game for them, obviously. So you can actually do this in a funny way, and maybe I'll leave you to think about how you do this. In other words, how you could convince your 5-year-old that you know where Waldo or Wally is, without actually revealing the actual position on the page. And that's another kind of example of how you could do zero knowledge. So maybe we'll discuss this afterwards, if someone has solutions. But the bottom line is this. So I've sort of hopefully convinced you, at least in one scenario, that you could have this protocol between two parties, such that one party has a secret and the other party is convinced that the first party has a secret without really learning anything else about it. What do you do with this? Well, imagine if this this sort of public message was actually, public value is actually a signature, and signature attesting to something, saying that, hey, I owe someone $5. And the secret value was a message and a key that sort of signed the message. And you know, without having the message or the key, you really can't sign these messages, right? We know that from integrity. You can prove that you actually signed something without revealing exactly what you signed, or without even revealing the identity of like who you are as a signature. You can say, I have the secret key that would sign this message, but I'm not going to tell you what the secret key is. And what do you do with this? You're like, okay, is this useful? Well, it turns out you can go from sort of cryptocurrencies that don't protect your privacy to cryptocurrencies that do protect your privacy. You can convince someone that, hey, I actually am the true owner of this coin, without actually revealing who you are. And if you've heard of Zcash, this is sort of built on these kind of technologies in a succinct way. And I was making a joke earlier that you cannot finish a talk in the Valley these days without talking about cryptocurrency. So here's my cryptocurrency plug. But so zero knowledge proofs have been used for a lot of other things. They're used, for example, for you to identify that you have a valid device, I don't know, like a key or something like that, like a car key, without actually revealing maybe the exact car that you have. So just so that maybe dealers can't like cheat it, or they cannot copy it over. Or you have devices that are out there and you want to know whether this is a valid MacBook or not, without actually revealing your serial number and so on and so forth. Then you can actually say that, yes, I do have a valid signature or a valid blob from Apple, without actually revealing what my, say, username and password is, or what my exact registration ID is. So these are examples of what are called anonymous credentials that also use zero knowledge proofs. So they're used in a lot of very cool, interesting places. So with that, I'm going to conclude. So in this talk, what have we talked about? We talked about several aspects of user data. We have talked about how to kind of protect them in various ways, how to treat user data the right way. I think if there's any takeaway from this talk, it's going to be that you sort of choose what works best for you. Keep these ideas in mind. There are many ideas. There are a lot of interesting ways to sort of apply them. Companies are doing it today. These are all not just kind of ideas out in the air. People are working on it every day. Privacy, security, and cryptography are typically not at odds with getting things done, which is a good thing. Otherwise, I wouldn't have a job. So you can actually kind of keep things secure and still have a robust company that's running. And it only gets more difficult as you grow bigger and bigger. And like if I kind of steal from an old proverb, sort of the best time to get started is during the design phase when you're thinking about the project. But the second best time is to start now, is to kind of think about these problems now as you continue to grow and kind of see what ideas, kind of what of these ideas, or which of these ideas would work best for you. So with that, I conclude. I'll take any questions, including why my email is that.